Hi, folks. Today we're going to talk about measure theory. Measure theory is a big one, and so this one might go a little long. Let's see how we do. And so measuring things. While metrics are a good approach to measuring, it's not the only way to measure things. This is where measure theory comes in. So given a set, whether abstract or the number line, it would be nice if we had a way to measure in a more general way. To do this, we're going to need a topology-like structure to play with, and measure theory develops the underlying structures of both calculus and statistics. It's kind of the big picture for what we're doing today. But throughout everything that we're doing today, I want you to think about this idea. The metrics that we explored last time, they were all about measuring distance. In this case, we want to think about it more like eating a tub of ice cream. And so if you are taking out spoonful after spoonful of ice cream, well, there's a lot of different ways you could take that ice cream out of the tub. Uh, all of the ice cream that you take out would equal the entire total of the ice cream, right? Well, we need to find some way to formalize all of the different ways that we can take the ice cream out of the ice cream container. And now that I've said that, I just want to eat some ice cream. So let's get on to it. And so we're going to begin with this idea of a sigma algebra. And so a sigma algebra is a structure which is very similar to a topology, but with one big difference. And so let's refresh what a topology is. And so a topology on a set X is a collection T of subsets of X having the following properties. The empty set and the whole set must be in T. The union of elements of any subcollection of T is in T, and the intersection of any finite subcollection of T is also in T. A set X for which a topology T has been specified is called a topological space. This is really our basic space. This is our way of describing some collection of objects, and we've been using it throughout the entire semester. This is where we always go to whenever we need to describe some object. And so ultimately, a topology is just a collection of sets. If you take any unions or finite intersections of sets, you get another set in your collection. And here's an example. If you've got set X, which has 1, 2, 3, 4, then we could create a topology which looks like this. We have the empty set and the whole set. We've got 1, 1, 2, 1, 3, and 1, 2, 3. If we take the union of any of these elements, we're going to get another element of this set. And so, for instance, if we take 1, 2, union 1, 3, we get 1, 2, 3. If we do the intersection, we're going to get another different set. And so 1, 2 intersect 1, 3, we get 1. And so this is a very good structure. We've been able to do a lot with it, but we need something new. And to do this, we're going to have to talk about complements. And so consider this example, which is the example we just did. It's a topology because it includes all unions and intersections. While unions and intersections are always included in a topology, it does not guarantee that the complement of a subset will be in the set. And so if you recall, a complement, if we are given some universal set, the complement of A, written A prime or U minus A, is the set of elements in U which are not in A. And so in the case of this topology, the complement of 1, 3 would be 2, 4, because the whole set is 1, 2, 3, 4. Well, if we have 1, 3, we would still need 2, 4. Well, 2, 4 is not in here. Same with 1, 2, 3. If we have 1, 2, 3, we would really want 4 to be included in here. And so what we need is a new structure which includes all of these complements as well. And the motivation for this is thinking of the ice cream example. If we take a spoonful of ice cream out, what are we left with? Well, we're going to be left with the rest of the tub of ice cream. Well, in this case, if we take this topology, if we remove the set 1, 3, what do we have left? Well, we'd be left with the set 2, 4, but 2, 4 isn't part of our topology. And so we really want to have that complement included in our set of sets. Another example, and this is a common one, is the idea of the butcher shop analogy. And so when we are measuring a set, if we measure one subset, we want to be able to figure out the measure of what's left, which is the complement. And so the common analogy is the butcher shop. When we cut meat into steaks, and we can see there's 4 steaks here, each steak has measure. If you want, you can think of it as a weight. But we would also like to know the measure of how much meat is left. And so this would be the complement. But also, what if we're just talking about these 3 steaks? And so if we only sell these 3 steaks, we would want to know the complement of what's left for that. And so for any collection of steaks, we would want to know what's left. And so we need to have the complement of any element of this set. And that's what a sigma algebra is. And so a sigma algebra is a topology-like structure which we use to build measures upon. It gives us different subsets, but also the subsets of what's left. And that's what makes it a little special. And so let X be an arbitrary set, and a collection T of subsets of X is a sigma algebra if, well, for one, X and the empty set have to be in this sigma algebra. For each set A in T, the complement A prime also has to be in T. We also have to have the union of elements of any countable subcollection of T and the intersection of elements of any countable subcollection of T. For our purposes, we need to have unions, we need to have intersections. Often we use a sigma symbol or this funny looking A to represent the collection of sets. For our purposes, we're going to simplify things. We're already familiar with the idea of T as a collection of subsets of X. We're going to use that to represent our sigma algebra as well. If you want to know the key differences between a topology and a sigma algebra, I made ourselves a little Venn diagram to highlight it. And so in both cases, both topology and a sigma algebra, they include the whole set and they include the empty set. They also both include unions, and they also both include intersections. But how many unions and intersections is a little different. The key difference, though, is the idea of complements. And so a topology does not require that complements of subsets be included, whereas a sigma algebra requires the complements be included. Yeah. If we are dealing with a set of finite elements, a sigma algebra is guaranteed to be a topology. But a topology is not guaranteed to be a sigma algebra. So we can think of it that way, as a sigma algebra as being a stronger form of a topology. Let's look at a finite example. And so let X be 1, 2, 3, 4, and consider a collection of subsets T, which is the empty set 1, 2, 3, 4, and 1, 2, 3, 4. Let's verify that this is a sigma algebra. And so to be a sigma algebra, it must include the empty set and the whole set. That's definitely there. We have to include complements. And so the complement of the empty set's the whole set. The complement of 1, 2 is 3, 4, and vice versa. And so all the complements are taken care of. It also includes all unions and intersections, because 1, 2 union 3, 4 is the whole set, and 1, 2 intersect 3, 4 is the empty set. And so this is a sigma algebra. And we can start to see how things are divided here. We can see that we have 1 and 2, which are kind of coming together as a set. And then we have 3, 4, which are coming together as a set. It's almost as though we've divided the set in half. Half of it is going into one section, and the other half is going into this other set. Here's another practice problem. Let X be 1, 2, 3, 4, and consider a collection of subsets T with the empty set 1, 1, 2, and 1, 2, 3, 4. This is a topology, but it is not a sigma algebra. And so how many more subsets would we need to add in order to make this into a sigma algebra? And so we would need to have to ask ourselves is, what would all of the complements of these things look like? And so what's the complement of 1? What's the complement of 1, 2? What would the unions and intersections of all of these values now be? And so that's how we approach it. And so we start with the idea of the complements. Well, the complement of 1 would be 2, 3, 4. The complement of 1, 2 would be 3, 4. And so then we'd need to look at the unions and intersections of all of these values. And so if we have 1 and we have 1, 2, and we have 2, 3, 4, and we have 3, 4, well, we could take 1 and 3, 4. And so that would give us 1, 3, 4. So we have to have 1, 3, 4 included in this set. And we would also need the complement of 1, 3, 4, which would be 2. And so now we get this, which would be our sigma algebra. We would have 1, 2, 1, 2, 3, 4, 1, 3, 4, 2, 3, 4, and 1, 2, 3, 4. This would be a sigma algebra, which would include this topology within it. Now, looking at this, we can start to look at the structures again. Can we start to see how things are being divided? Are there a pair of numbers which are always going to be paired together? Are there certain numbers which we could section off? Well, that's the characteristics of a sigma algebra. And so consider the sigma algebra, which we just came up with. 1, 2, 1, 2, 3, 4, 1, 3, 4, 2, 3, 4, and then 1, 2, 3, 4. When we think of the butcher shop analogy of the sigma algebra, what characteristics do we notice? Well, if we separate out the 1 from the set, the remaining piece, 2, 3, 4, remains. And in fact, we could remove the 1 completely from the set. If we removed every single term that had a 1, that would mean get rid of the 1, get rid of the 1, 2, get rid of the 1, 3, 4, get rid of the 1, 2, 3, 4. Then we'd be left with the empty set, 2, 3, 4, and 2, 3, 4. This new set is itself a sigma algebra. We can also start to see how things are separated. And so this whole set, 1, 2, 3, 4, we could divide it up into a bunch of different ways. We could cut it up so that it's a 1, a 2, and a 3, 4. Or we could slice it so that it's a 1 and a 2, 3, 4. Or we could slice it so it's a 1, 2, and a 3, 4. Or we could make it so that it's a 1, 3, 4, and a 2. All of these different ways are ways that we could divide these elements up so that we would still be able to get the entire set out of them. But these are disjoint, and the values are all going to be the complements. All of these values have their complements within here. And note that regardless of how we slice the steaks, the 3 and 4 are always going to remain together. And so in this case, we're never going to be dividing this up in a way where the 3 and 4 are separated from one another. And so this is one of those things that happens with a sigma algebra. We've now essentially defined all of the different ways that we can break up this set. For a bigger version, let's talk about the real numbers. And you don't have to get into the weeds on this too much, but we're going to talk about the Borel algebra. And basically, this is the standard way to define a sigma algebra on the entire real number line. And so what we've done so far is just finite examples. If we want to figure out ways to cut the entire real number line, this is it. And so any interval of the form AB, or half open interval, this will be included in our set. And so note A or B could be infinity on these intervals. And so if we're talking about something from 2 to 3 where we're including both endpoints or not including both endpoints, we're going to be including that in our Borel algebra. We're also going to be including any individual points. And so if we're talking about the number 2, 3, 7, pi, it doesn't matter. Any number, any real number is going to be a part of this sigma algebra that we're creating. And then we're going to take all combinations of unions, intersections, and complements of these sets that we have created. This is framed as a master set, which includes just about anything. and we can divide it into a whole number of different ways. And so this is a very structured way of approaching the real numbers. And so examples of things included the natural numbers, the whole numbers, the integers, the rational numbers, and the irrational numbers would all be included in the Borel algebra. And so in this sigma algebra. But also things like the union of all closed intervals, which go from even numbers to their next odd numbers, would be included in this Borel algebra. Really, it's difficult to come up with examples of things which are not included in the Borel algebra. It's totally possible. I mean, I'd go and start looking at a Cantor set or something. But for now, it's tricky to try and visualize what things might not be included in this. And so we have a sigma algebra, which we can use in general for the reals. We can cut up the reals however we want, and it will be okay. And so now that we have the idea of this highly structured set, how do we measure things? Well, let's define what we mean by measure. And again, we're going to go back to the idea of the ice cream or the butcher shop model. And so let X be a set and T be a sigma algebra over X. A function mu, and so that's the Greek letter mu, from T to R is called a measure if it satisfies two conditions. And so the first is non-negativity. And so for any element in T, the measure of this the measure of this subset is greater than or equal to 0. And the measure of the empty set must always be equal to 0. And so everything has to be positive. When we are measuring, we are not going to be measuring and getting negative values out of this. The other requirement is countable additivity. And so the measure of the union of any countable number of disjoint sets is equal to the sum of the measure of the individual sets. If you want to think about this in the ice cream analogy, what this is saying is when we take out one spoonful of ice cream and add it to our bowl, and then we take out another spoonful of ice cream and add it to our bowl, we now have 2 spoonfuls of ice cream. Those 2 spoonfuls, they didn't have anything in common when we were taking them out of the carton. And so whatever measures we had for those 2 spoonfuls, well, now we have those 2 spoonfuls in our bowl. Yeah, countable additivity works like the butcher shop analogy too. And so if we measure 2 sets in T and they don't have any elements in common, then the measure of the union of those 2 sets is the same as the sum of the measures of the individual sets. In butcher terms, when you weigh 2 steaks, they don't have any steak bits in common, and so we can just add the weights of the 2 steaks individually to get the total weight. And so that's not a high bar to hit, but this allows us to define things in terms of weights, but also in terms of volumes and in terms of a number of other things. And so this idea of measure is a very general approach to how we can measure things. And so here's an example. Let X be equal to 1, 2, 3, 4, and consider a collection of subsets T, which is the empty set, 1, 2, 3, 4, and 1, 2, 3, 4. We already showed that this is a sigma algebra, so we don't have to worry about that. Let's define our measure on this as a measure that counts up the number of elements in a set. Let's verify it's a measure. And we call this the counting measure. And so looking at this, we have to make sure it's non-negative. And so if we are just counting up the number of elements in any given set, well, the empty set has no elements in it, so its measure would be 0. The set 1, 2 has 2 elements in it, and so its measure would be 2. The set 3, 4 would have 2 elements in it, so its measure would be 2. The total set would have a measure of 4 because there's 4 elements in it. And so the other thing we can do is countable additivity. If we think of 1, 2, and 3, 4, well, 1, 2 has a measure of 2, and 3, 4 has a measure of 2. If we add them together, or if we take the union of them, we get the whole set, which has a measure of 4. And sure enough, 2 plus 2 equals 4. And so it checks out. This is a way of measuring this sigma algebra. And this might be a way that you would apply a measure to your ice cream analogy. How many scoops are in the bowl of ice cream? Well, every time we take a scoop out, we're counting that as one. And so that's one way in which we can measure ice cream. Here's another way. And so same set, but now we're going to define the measure as the measure that adds together all of the values in a set. And so here, this set has 1 and 2, and this one has 3 and 4, and this one has a 1, 2, 3, and 4. Let's verify this is a measure. And so again, the measure of the empty set is 0 because there is nothing in there. And so we have no elements, its measure is 0. Otherwise, we know that the measure is going to be greater than 0 because we can add up the elements in all of them. Well, let's figure out the measure of each of these elements. For 1, 2, the measure of these elements, or the measure which adds together all of the values in the set, 1 plus 2 is 3. And so the measure of 1, 2 would be 3. The measure of 3, 4 in this context would be 7, because 3 plus 4 is 7. The measure of 1, 2, 3, 4, well, 1 plus 2 plus 3 plus 4 gives us 10. If we're taking the union of these two sets, we get this set, and 3 plus 7 equals 10. And so we have the countable additivity. Here's a messier example. We've already seen this sigma algebra also, and so this is the one which is 1, 2, 1, 2, 3, 4, 1, 3, 4, 2, 3, 4, 1, 2, 3, 4. Let's define the measure as a measure that adds together all of the values in a set. And so this set is 1, this is 2, this would have a measure of 3, this would have a measure of 7, 1, 3, 4 would have a measure of 8, 2, 3, 4 would have a measure of 9, and 1, 2, 3, 4 would have a measure of 10. Let's verify that this is countably additive. And so to verify that it's countably additive, we just have to show that we can take all of the pieces or all of the disjoint sets and add them together. And so if we take 1, 2, 3, 4, or 1, 2, 3, 4, or 1, 2, and 3, 4, or 1, 3, 4, and 2, well, all of those are going to give us a measure of 10 because we can add up all of the different values individually. The only other combinations that we have would be 1 and 2. Well, 1 plus 2 is 3, and that would be the measure of 1, 2. 1, 3, 4, which would be the same as the measure of 1, 3, and 4. And 2, 3, 4, which is a measure of 9. So it's very easy to double check that in every single case, we are getting countative additivity. Here's a quick sidebar, something to introduce at this point. You could have introduced it at any point, but we want to have a way of defining minimum because we don't really have a good way of defining minimum when that minimum value doesn't exist. And so we're going to call it the infimum. And so the infimum is sometimes known as the greatest lower bound of a set. The idea being if we have something which is going from 0 to 5, but not including 0, but it includes something like 0.001 and 0.000001 and all the way down, but it doesn't include 0. Well, we would say the infimum of that set is 0 because it includes everything down to 0, even though it doesn't include 0. And so it's the minimum, even if the minimum doesn't exist. The supremum is the same idea. It's the smallest upper bound. And so it is the smallest number which is greater than or equal to everything in a set. And so here's an example. Consider the set of numbers of the form 1 over n for natural numbers n. There is no smallest value. There's no minimum for this set because you get 1/2, 1/3, 1/4, 1/200th, 1/2 millionth, 1/2 trillionth, and on and on and on. So there is no smallest number. But we would have an infimum. And so the infimum would be 0 because the values of this will get really, really close to 0, but they'll always be a little bit greater than 0. And so the values of 1 over n will always be greater than 0, and 0 is the largest number where this is the case. The reason we need infimum and supremum is sometimes when we're trying to measure things, we end up getting some weird sets. And that's where this idea of Lebesgue measure comes in. And so consider the Borel algebra on R, which consists of intervals, points, and their countable unions, intersections, and complements. And so for an interval E from A to B, or AB, or some half-open interval, we're going to define the length of the interval as L of E is equal to B minus A. And so our measure of any interval is always just going to be subtract the endpoints. We can also allow L of E to be infinity. And so if we end up getting something which is an infinite distance, then we're just going to say it's infinite. Any individual points will be said to have measure 0. Now, this definition is what we're going to call Lebesgue measure. And so Lebesgue, if you want. Oops, I went too far. There we go. And so for these sets, we will define the Lebesgue measure using this lambda, a Greek letter, to be equal to the sum of all intervals, or all of these interval lengths. If a particular subset isn't an interval or isn't a countable collection of points, we have to get creative. And that's where this idea of infimum comes in. And so let E be such a set. And so a set which isn't an interval and it isn't a countable collection of points. Then we consider a countable collection of disjoint open intervals which contains E. And we call this a covering. And so something which has this thing in it. Since we can measure intervals, we can measure this countable collection of intervals. Formally, we define the Lebesgue measure to be the infimum of the measurements of all possible coverings of the set. That's kind of high-end stuff. I would not stress it too much. It's something which we use every now and again when we're dealing with really abstract sets, again, such as the Cantor set. How do we measure things which don't really seem like they could be measured? What if we have an uncountable number of disjoint points? What's the measure of that? Well, this tool allows us to measure stuff like that. And so for simple sets like this one, let E1 be 0 to 0.25, 0 to 4, or 0.4 to 0.5, and then these two individual points. Well, we can just measure the two intervals and add them together. And that's what our Lebesgue measure will give us. And so in this case, the measure would be 0.25 plus 0.1, which is 0.35. If we have something weirder like this, let E2 be the union of all intervals of the form n comma n plus 1 over 2 to the n, with n being the natural numbers. Well, this would be going from 1 to 1.5, then 2 to 2 1/4, then 3 to 3 1/8, and 4 to 4 1/16. The measure of this would be a geometric series. And so we actually have already done this one before. The measure of 1/2 plus 1/4 plus 1/8 all the way down ends up being 1. Where Lebesgue measure comes in handy is when we're trying to measure things like the rational numbers. And so the rational numbers, it's a countably infinite set of points, but they're everywhere. And so between any 2 points, you're going to find a rational number. But because the rational numbers are just a countable set of points, we would say that their measure is 0. And so you could condense them all down into nothingness. If instead we think of the irrational numbers, and let's just say the irrational numbers between 0 and 1, well, we know that the complement of the irrational numbers would be the rational numbers, and the rational numbers have measure 0. And so the irrational numbers would have a measure which includes the entire space. And so the measure of the irrational numbers on 0, 1 would be 1. And so this tool, the Lebesgue measure, it gives us a way of measuring really abstract things that we might not have thought about how we could measure them. And it helps us understand that when we're talking about countable and uncountable things, there's a very big difference in how we can look at them. The rationals, between any two rationals, there's an irrational number. Between any two irrational numbers, there's a rational number. But there are so many more irrational numbers that the rational numbers we can think of as a measure zero set, while the irrational numbers end up taking the entire measure. One more big topic we want to introduce on this idea of measure is the idea of Riemann sums. And we might even get into the fundamental theorem. And so Riemann sums are how do you find the area under curves? Now, we've been talking about how we can measure stuff. Well, how would you measure the area under a curve? The Riemann sum approach is to try and break it into rectangles. And so suppose that we have some function in R2. If we wanted to figure out the area under it, what we can do is we can break the x-axis into some series of intervals and then use f of x, our function, to define the height along that interval. If we add together these areas, we will get a good approximation for the area. And we call this the Riemann sum. Now, the Riemann sum is a very powerful tool, but it does have some drawbacks. Let's talk about some of the technical stuff first, though. And so given a function, technically we're using our sigma algebra to break the interval up. And so if we're going from A to B, we can break it up into partitions using this idea of the sigma algebra. We can then define the Riemann sum using our sigma notation, our summation notation, and say that it's the sum of all of the areas with a height at some value and some base distance going across. And so this is just height times base, and then we're going to add up all of the rectangles together. Is a Riemann sum a measure? Not really, for two big reasons. For one, if this function is going negative at any value, if it has negative values, then our function's area would actually be negative. It's okay for us to have negative values for an area, in particular because it would be representing that the function is going into a negative region. But we're not allowed to have negative values for a measure from a measure theory perspective. The other issue is a general Riemann sum is not well defined. We're saying that we can choose any value from this interval and get an f of x from it. And that's a very large problem. And so generally, when we're talking about Riemann sums, we try and define them a little bit better. And there's a lot of different types of Riemann sums. We can define Riemann sums based on the left endpoint. And so in that case, we're just choosing the left endpoint to determine the heights of these rectangles. We can use the right endpoints. And so, I went one too far. And so we can use the right endpoints to determine the heights of these rectangles. We can use the midpoints to determine the heights of these rectangles. We could choose the highest point on each of the intervals to determine our Riemann sums. We could choose the lowest points on each of these intervals to determine our Riemann sums. We're still just approximating with rectangles, and as long as we know how many rectangles we're using, we can choose the high, the low, the left, the right. It doesn't matter. The more rectangles we use, the better the approximation is going to be. And it turns out this is regardless of the Riemann sum we use. As long as we fix the distance between, or the base of the rectangle, we're always going to get better and better approximations as we use more and more and more. And in fact, if we take the limit, if we make it so that we are using an infinite number of rectangles, which are infinitely thin, we end up getting the exact area for whatever the region is under the curve. And that's really the power of a Riemann sum. If we take an infinite number of rectangles, we can get the exact area under a curve. And so the limit of the Riemann sum is important in calculus, but it can be very cumbersome to write. And so we do have a new notation if we want to play with it. Instead of writing this out, the limit of the infinite sum of these rectangles, we'll often write it in this format, where we call this the definite integral. And so this would be the definite integral from our starting point to our ending point. So here's our starting point, here's our ending point, and this right here represents the area under this curve, as approximated by an infinite number of rectangles. Well, this now gives us a tool for calculus. And so recall the derivative. Do y'all remember the derivative? Given a function we call the derivative f prime of x, the function which gives the instantaneous rate of change at every single point. It is the rate of change. It's a measure of how things move, grow, or otherwise change, but really it's just the rate of change. And keep that in mind. The derivative is the rate. The reason I want to emphasize that the derivative is the rate is because we also have something from Algebra 1, which relates distance, rate, and time. Your distance is equal to your rate times your time. If you're going at 5 miles per hour for 3 hours, your distance traveled is 15 miles, because 5 miles per hour times 3 hours gives you that 15. We can actually visualize this very nicely using a graph. And here's the graph of this. If we are running for 3 hours and we are going at a rate of 5 miles per hour, the area under this curve would correspond to our distance. So distance equals rate times time. Well, suppose you go for a 3-hour run from 1 p.m. to 4 p.m., and you know your speed at any time during your run using a smartwatch or something. Then the area under this curve will tell you what your distance traveled is. And so if this is your rate at any particular time, your speed, your velocity at any given time, then the area under this rate curve is going to tell you what your distance is, because distance is rate times time. More importantly, rate in this case is actually the instantaneous rate of change of your distance, meaning rate is equal to d prime of t. It's the derivative of your distance. And so this means that we can rewrite the distance as the area as the integral from a to b of d prime of t. And so the area is the Riemann sum of this distance, or the derivative of this distance. Here's the thing. There's another way to measure distance traveled. If you've been running for, or let's say, if at time, let's see, if at time A, you are 2 miles into a trail, and at time B, you are 17 miles into a trail, then the total distance you've traveled is 15 miles. Basically, the distance at the end minus the distance at your start is going to be your total distance. When we include this with the previous formula, we get that area, the integral from d prime of t dt, is just equal to your distance at your endpoint minus your distance at your starting point. In calculus, we call this the fundamental theorem of calculus. It gives us a way to find the area under any curve. Let's see how it works. And so let's consider the function f of x, which is equal to 1/3 of x cubed on the interval 0 to 3. We know the derivative of this function is x squared, and that's something that we have from calculus. By the fundamental theorem of calculus, the area under x squared on the interval from 0 to 3 would be determined by the antiderivative. And so if f is 1/3 x cubed, well, the integral of f prime would be equal to f of 3 minus f of 0. This means that the area under this curve from 0 to 3 could be evaluated by just plugging 3 into this function and then plugging 0 into this function and subtracting. When we do that, we get 9. And so the actual area under this curve from 0 to 3 is 9. That's a very handy trick. And it's a tool which is used in calculus to find the area under curves. And we use it to do a whole bunch of other things. And so applications of this fundamental theorem, the fundamental theorem of calculus gives us a way to calculate the area under curves, but it also gives us motivation to undo a derivative using what we call an antiderivative. And so since we can model many things using a derivative, this tool gives us a way to solve equations where we know things about how things move, grow, or otherwise change. If we know the rate of change of bunnies, we can calculate the number of bunnies. If we know the rate of change of wolves, we can calculate the population of wolves. We also see this a lot in statistics. And so much of statistics relies on an understanding of the bell curve, which is a function shaped like a bell. It's actually a function transformation of e to the negative x squared. Well, given a Riemann sum, we can approximate the area under the curve, which can tell us how far from the mean we've deviated. Some form of standard deviation or something. It can tell us the likelihood of certain things, including whether certain things are truth or lies. As we approach the end of our lecture series, we're going to be focusing on this idea of truth and lies, and understanding statistics from a measure theory perspective is a big part of that. We also have applications related to commerce. And so fundamentally, all commerce is a structure of measure theory. When we think the butcher shop, there is a measure, which is known as the price, associated with each steak. Any set of goods has a price. Barring sales for bulk purchases, this measure is countably additive. Other things which approach a measure include our justice system, the education system. And so here's the question: is grading assignments a measure? And if so, what would the sigma algebra be? How do we determine whether something is worth 5 points or 4 points or 2 points? Do we have a rubric? And when we're thinking about that rubric, what would the algebra be on that? Final thoughts. We've covered a lot today. Metrics and measures give two very different structures from analysis for exploring what it means to measure something. A metric can measure the difference between two elements in a set, while a measure can assign a quantity to the set and subsets themselves. Depending on what you're doing, one may be better than the other, but both do have value. Looking at what we've learned up to this point, we have now explored all 5 of the major branches of mathematics. We've explored discrete math and number theory. We've explored topology. We've explored algebra. We've explored geometry. And now we've done a pretty deep dive into the study of analysis. With all of these pieces together, we can now explore an even more interesting structure. And that structure is chaos. When we think about all of these structures, we've seen how they can go good. Now we're going to be looking at how they can go bad. With that, I will let you get to work exploring where you find measures in the real world. Good luck, folks.